Hello, everyone, and welcome to online lecture 17. Today, we will be discussing a new test, the t-test for a single sample. But before we get into all of that, I first want to offer a word of congratulations because you have now survived, I would say, kind of the worst part, the most challenging part anyway, of the course, in that you have all the basics now. Okay, you know about means and standard deviation and standard errors of the mean and all of that good stuff. So at this point, since you have all the basics, what we're going to do is we're going to take each test that we learn and then tweak it, change it in some form or fashion to get a new test. Okay, and that's what we're going to really do today. We're going to tweak what we learned last time about the z-test to get this new test, the t-test for a single sample. So let's start by just reviewing the z-test a little bit. Now, one thing you may not have noticed, but is pretty important to notice about the z-test, is that it compares a sample to a population. It compares a sample to a population. Now, not all the tests we learned about are going to compare the same thing. In fact, that's going to be an important way to differentiate among some different tests. We'll be knowing what we're comparing to what. So watch that trend. Now, for today, it won't matter, but in the future, it will. So I want you to watch that trend of what we're comparing what to what. Okay. So we were comparing a sample to a population. So as we go on with our inferential testing, with the t-test for a single sample, we'll also compare a sample mean to a population mean. So that's what's going to be what's in common. They both have the same goal. Okay? The population mean is known for both. We know what mu is. We're given mu for both z-test and t-test for a single sample. Still, just showing what they have in common. However, for the z-test, the population variance is known. And for the t-test for a single sample, the population variance is unknown. This is the big discriminator between these two tests. This is what you can use to really know which test is which. And that's an important piece to know for this class, which test is which. Okay. So what do we mean when we say the population variance is known versus the population variance is unknown? Well, we mean that you know some form of sigma. Remember the O with the little hat on the end of it? We know some form of that. We either know the population variance, sigma squared, or we know just plain old sigma, which is the population standard deviation, or we know sigma of x bar, population standard error of the mean. If we know any of those, we are going to say that the population variance is known. Okay, so we're looking for one of those three. Now you might be wondering, well, why is it okay to have one of those three? Because the truth is, if I know any of those three, I can get back to population variance, right? And just for an example, if I know sigma, if I know the population standard deviation, how do I get back to population variance? I square it. I square it and I'm back to population variance. So as long as I know some form of sigma, we're going to be looking at that z-test that we were looking at last time. And if I don't know a form of sigma, but I am still comparing a sample mean to a population mean, and I know the mu, then I'm looking at a t-test for a single sample. Okay, so that's how we differentiate the two. Okay, so as we said, it's very similar to a z-test, except we don't know the population variance, right? So what are we going to do? We're going to estimate it. We're going to estimate the population variance because we need that information in order to proceed forward with calculating a statistic. So you might be wondering, how are we going to estimate that population variance? What do we have that's available to us that we could possibly use to estimate the population variance? It's the sample variance. So we're going to take our sample variance to estimate our population variance. And we'll talk more about that. The other thing that's going to be new is we're going to use a special non-normal table to find cutoff scores. So you've already been introduced to the Z table, which you can use to find cutoff scores for the Z test. Now I'm going to show you the T table, which you use to find cutoff scores for the T test. I will tell you that most students find the T table to be preferable to the Z table. Okay. Also, while the sample distribution of the dependent variable may not be normal, we are going to assume that the population distribution of the dependent variable is normal. So we're making an important assumption for the t-test for a single sample, that the population distribution of the DV is normal. Okay, and that's going to yield us certain benefits. We're going to be able to use that information from the central limit theorem. All right. So here's our variance problem. I already shared with you that I'm going to use the sample variance as opposed to the population variance to get an estimate of the population variance. I'm going to use that sample variance. But here's the problem. On average, the sample variance tends to be smaller than the population variance. And we saw that before. We actually noticed that before when we were calculating variances and standard deviations, how the sample variance was a little bit, would tend to be smaller. So we need it larger. So what do? We divide by n minus 1. So if you were wondering back when we were talking about n minus 1 on the bottom versus n for our population variance, if you were wondering about that, it's all because we want to bump up our sample variance, bump up our sample standard deviation so they're actually larger than the population of that. Okay, so that's why we divide by n minus 1, and that's why, even though we just said that it would on average be smaller, while we actually saw larger values for our sample variance and sample standard deviations compared to our population variance and population standard deviation. Okay, so here is our SUSAD formula once again, right? We subtract, then we square, then we add, then we divide. Now, one way to abbreviate the top part of this equation is with the symbol SS, which stands for sums of the squares. Now, to be really accurate, we would say SS stood for sums of the squares of the deviations. But for short, we just call it sums of squares. So if you see sums of squares, know that we're still talking about sum of the squares of the differences or deviations. Okay. So now we're going to talk about this new concept called degrees of freedom. Now, while we haven't talked about it yet, we are going to talk about it going forward for many of our statistical tests. And what it is, it's the number of scores that are free to vary. And what we can define it as, or show it as, is that if all the deviation scores are but one are known, the last score can only have one value. So I'll give you kind of a theoretical example of this. I'll give you one that's actually more in line with the math of what we're doing, and one that gets at it but is less in line with the math of what we're doing. doing. So let's start with the less one first. Okay. I want you to consider the game of baseball. We understand the field of play consists of 9 positions. Now, the coach of a particular team is free to assign any of the 9 players to any of the 9 positions. So let's say they go ahead and do this. They assign player 1 to be catcher, player 2 to be pitcher, player 3 to be shortstop, and so on and so forth. Now, once the 8th player is assigned to the 8th position, does the 9th player need to really wait around to see what position they're playing? Well, no, it's predetermined, right? They don't have a choice. In other words, the coach is not free to pick the last player's position. If every position is played except for right field, then we know that that's what the last person is playing, right field. Okay. Now you can also think of it like this, that for every position that is assigned, the remaining number of choices, the remaining number of decision options is decreased by 1. In other words, 1 degree of freedom or decision option is lost every time a position player decision is made. So when considering the last position and player, there is no choice of selection or assignment, simply because the total number of positions and players is fixed in advance. Okay. So that's the baseball example. Now, if you like that one, good. If you don't like it, because it doesn't have enough math in it for you, let's try something else. Let's say you have a sample of 3 numbers. And I'm going to tell you 2 of them. One is 10, one is 30. And I also am going to tell you that the mean is 20. So you have 2 numbers, one that's 10, one that's 30, mean is 20. Can you pick any number you like to be the remaining number? No, because it's got to work out so that the mean is 20. In fact, the only number you can choose, or you really don't get to choose, the only number that can be the third number is 20. And that's how we lose degrees of freedom. Okay. All right. So our degree of freedom here is n minus 1. Sample size minus 1. We just lose 1 degree of freedom because we're really just calculating one piece here. We only have one mean we're working with. So we lose 1 degree of freedom. Okay. So since our degree of freedom is n minus 1, this means we can actually rewrite the formula for the sums of squares, the sample sums of squares, or S squared, using, let me try that again. So the formula for S squared, or our sample variance, can be rewritten using sums of squares and degrees of freedom. So because I fouled that up, I'm going to say it one more time. So the formula for S squared, the formula for sample variance, can be rewritten using sums of squares and degrees of freedom. How? Remember, this is sums of squares. The top is sums of squares of the deviations or differences. That's SS. The bottom is n minus 1, which is really, as we saw up here, df. So that can be written as SS over df. Okay. So now we come to our t-test for a single sample and the formulas. So we have to calculate 2 things for the t-test for a single sample. First, we have to calculate the t-score. How do we do that? We take T equals X bar, or sample mean, minus mu, or population mean, over the standard error of the sample mean, right? Now we saw sigma of X bar, that was standard error for the population mean. This is standard error for the sample mean. Okay. So now we have this S of X bar, which is standard deviation for the distribution of means, or standard error of the mean for a sample. Standard error of the mean for a sample. All right. So how do we calculate standard error of the mean for a sample? How do we calculate S of X bar? Very similarly to the way we calculated sigma of X bar. We take our standard deviation, or in this case, S, over the square root of n. Remember before, for sigma X bar, it was sigma over the square root of n. Now it's S over the square root of n. So it's very, very similar. Okay. So before, when we were talking about z-test and distributions there was only one distribution, the normal distribution. But I already shared with you that t is a little bit not normal. So there is one t distribution for each number of degrees of freedom. And the greater the number of degrees of freedom, the closer the t distribution is to the normal curve. Okay, so let's think about that for a minute. As the number of degrees of freedom increases, what else is increasing? Sample size, because degrees of freedom is simply sample size minus 1. So as degrees of freedom goes up, sample size goes up. Okay, so the greater the sample size, the greater the degrees of freedom, the closer the t distribution is to the normal curve. Okay. And so, as I shared before, we're going to use this t-table, and we're going to locate the appropriate cutoff sample score for rejecting the null hypothesis in the t-table. All right. So let's look at these t distributions that we were talking about. So in the black filled line, we have the normal distribution. In the blue dashed line with the smaller dashes, we have a t distribution for df equals 2, which means the n only equals 3, right? Because df equals n minus 1, so 3 minus 1 gives you 2. Whereas in the larger dashed blue line, we have a t distribution of df equals 20, df equals, which means the n equals 21. So look at how not so normal our small dashed line is, the one with df equals 2. And look how much closer to normal once we get up to 21 this is. Right? So the closer, the bigger our n, the bigger our df, the closer we are with our distribution to normal. Okay. So with all that said, let's work through an example together. The post-traumatic checklist, or PCL, has a mu, a population mean of 30.12, and a sigma, or population standard deviation, that's unknown in the non-traumatized general population. The researcher believes that people in Moore, Oklahoma will have significantly different scores on the PCL than the general population. Notice this so far sounds very similar to our z-test setup, except our sigma is unknown before we knew our sigma. So we sample 16 people in Moore, Oklahoma who complete the PCL, and we obtain a sample mean X bar of 35.52 and a sample variance S squared of 64. Okay, and our alpha equals 0.05. Okay, So alternative hypothesis looks pretty much the same. People in the community of Moore, Oklahoma will have different PCL scores on average than the general population. And the null hypothesis is that people in the community of Moore, Oklahoma will not have different PCL scores on average than the general population. So when we are actually looking to calculate the t-score for a single sample, we might want to break down our steps a little bit, because this is a little different from a z-test where we're automatically always given sigma or sigma squared, something that we can easily use. Here, we may not be given any of that information. In fact, we may just be given raw data. So if we are given raw data, then the first thing we need to do is calculate the variance for the sample. We need to get S squared. How do we do that? SUSAD. Good old SUSAD. Subtract, square, add, divide. Subtract each of our scores minus the sample mean. And we do this as many times as scores we have. Square each of those values. Again, we're doing this as many times as scores we have. Then add them up, that we just do once. And then divide by n minus 1, also we just do once. Next, we have a choice. We can either keep with S squared to calculate the standard error of the mean and take our square root later, or we can take our square root right now. We can take the square, remember how we get standard deviation? We take the square root of the n thing to get S. So it's really up to us. Now, I prefer to just go ahead with my S squared and use this formula on the left to calculate the standard error of the mean. S squared over n, take the square root of the whole thing. Or if you like, you can think about this formula on the left for standard error of the mean, S of x bar, to be square root of S squared over square root of n. That's another way to think about it. Now this is useful to use if you're given S squared. But if you're just given S, you can use this formula. Very, very similar, right? Standard error of the mean now equals plain old S over the square root of n. So why are these two equivalent? Because we know that the square root of S squared is S. So these two tops are really the same. And the bottom square root of n is the same. So they're really telling us the same thing. And we might just choose the one that's appropriate. And then we come down to step 3, where we calculate the t-score, which is x bar minus mu over standard error of the mean for a sample. And then we calculate df equals n minus 1. Okay. So the question you'll have to ask whenever you're given a setup for a t-score for a single sample is, where do I start? Do I start with step 1? Do I start with step 2? Or do I start with step 3? And it all depends on what you're given. If you're simply given raw data, you're going to have to start with step 1. If you're given an S squared or S, you can start with step 2. And if you're lucky enough to be given the standard error of the mean, the S of x bar, you can start with step 3. Of course, if you're given the t value, well, there's nothing left to do. Your instructor probably made a mistake there, huh? Okay, so are you given raw data, step 1, S squared or S, step 2, or S of x bar, step 3? Okay. So let's look at our setup and decide where we need to start. Remember again that I think it's very useful to go to a word problem and pull out all of the information from that word problem and write it out. So I pulled out mu equals 30.12, s squared equals 64, n equals 16, and x bar equals 35.52. So how did I get s equals 8? If you're thinking I simply took the square root of 64, because s squared is 64, so s would be the square root of 64 or 8, you're absolutely right. That is how I got s equals 8. Okay, all right. So I don't have raw data, so I don't need to start with step 1. I also don't have s of x bar, so I can't start with step 3. Well, I guess that leaves me with step 2. And I do have an s squared, and I do have an s, so I'm all set. I'm totally fine to do step 2. So we're going to start by getting our standard error of the mean. Now remember, I could do square root of 64 over square root of n, or I could simply take 8 over the square root of n, which is what I'm going to do. So 8 divided by the square root of 16 is 8 divided by 4, which is 2. Now, to be really precise, I should have carried 4 decimals here. Now, I know that it's an even 2, so I didn't bother. But to do the right thing, I probably should have said 2.0000. Okay, carrying those 4 decimals until that last step. Okay. Okay, so now I rewrite the top, or I just add to the top, because really the only new piece of information I've added is s of x bar equals 2.0. So now I have that. S of x bar equals 2.0. And again, like I said, it should have been 2.0000. Now I'm ready for step 3, because I have all my information for step 3. So I'm just going to start filling things in. 35.52 for x bar minus 30.12 for u over 2.0000 for s of x bar is my t-score. That's going to be my t-score, whatever this works out to be. And then my df is going to be 16 minus 1. That's 16 the n minus 1. So remember, I'm getting 2 things out of this, t-score and degrees of freedom. Okay. So the top resolves to 5.4 over 2.0000. And again, this could also be carrying all the O's equals 2.7000. And my DF equals 15. And I don't think we need to actually carry decimals for DFs, because DFs are always integer numbers. They're always no decimal numbers. Okay. So I have an answer. Wonderful. So now what? Is this significant? Is it not significant? What's the story? Well, we need to figure it out using this table, our brand new t-table. And in order to do this, we have to answer 3 questions. Okay, anytime you go into a t-table, you have to answer 3 questions. First, was this one-tailed or two-tailed? Let's go back and look. Different. It was two-tailed. Next, we need to know our alpha. What's our alpha? 0.05. So two-tailed and 0.05. I'm going to flip forward to the table again, and then we're going to flip one more time. So we're on the right side where it says two-tailed tests, and we're going to be down the center column where it says 0.05 at the top. Now, the last thing we have to know is our DF. Do we remember that? Let's look back. DF was 15. 15. So let's go down to 15 and find the number there. The number there is 2.132. 2.132. Now, what we want to have happen is we want our 2.7 to be more extreme than 2.132. Is it? Sure. Sure. 2.7 is further in the tail, is more extreme than 2.132. Now, just for fun, let's suppose that we had said that this had come out the opposite way, that this had been negative 5.4 over 2.0, that this had been negative 2.7. Now what? Remember, it's a two-tailed test. So what happens is we're going to compare negative 2.7 to negative 2.132. So this is one thing that the t-test has in common, or the t-table has in common with the z-table. It only shows you the positive values, but you can pretend all these values in the body of the table are either positive or negative. So does negative 2.7, is that more further in the tail, more extreme than negative 2.132? Sure is. Sure is. So we're looking for a number that's either more positive or more negative than what's in our table. Now that's true for two-tailed tests. But suppose this had been a one-tailed test. Then we have to watch the direction, right? Let's go back here. Then we have to watch. If we said that the sample mean of more would be higher than the population mean, then we got to look at our two means and decide, is 35.52 higher than 30.12? Yeah, it's higher. Okay, so I got the direction right. Or if I had said that the mean for our sample of more would be less than the population mean, well, is 35.52 less than 30.12? No, it's not. We got the direction wrong. At this point, you actually don't need to do any more calculations to figure out whether or not we're going to reject the null, because we're never going to reject it because the direction's wrong. Okay. So if your direction is correct, then it's one-tailed. Or if it's simply two-tailed, you have to go through all the calculations to know the answer. But if your direction is incorrect, stop right there. You're not going to reject the null. Okay. So let's review. To reject the null hypothesis, we want our calculated t-score, right? That t-value we get, to be more extreme, to be further in the tail than the table's value, which means more positive or more negative than the table's value. But the exception to the rule is if you have a one-tailed test with results in the opposite direction of your alternative hypothesis, you will not reject the null. So the order, it has to match. The direction you claim has to match your results, just like we've been talking about. And I keep emphasizing it because it is that important. Okay, and because we are going to have this rule throughout the rest of the course. So it's a good one to try to get a handle on. Okay. So the last big topic I want to talk about is alpha versus P. And we've been talking about alpha for a little while now. And if you remember, alpha is our a priori or predetermined cutoff level. It's the probability with which we will tolerate a type 1 error. And it's often set to 0.05 or 0.01. Okay, so you can think of alpha as our tolerance. I'm willing to make a type 1 error up to 5% of the time if I set my alpha to 0.05. Now, P, on the other hand, P always stands for probability. And P is the probability of obtaining a test statistic at least this extreme if the null hypothesis were true. Or you can think of P as the probability of making that type 1 error. Okay, so alpha is the tolerance for the type 1 error. P is the probability of actually making that type 1 error. And so when we reject the null, we are concluding that P is less than alpha, that our probability of making a type 1 error is less than our tolerance. In this case, is less than 0.05. Okay. So absorb that. And that is all I have for you for today. Stay well, take care, and I will talk to you next time.